All right, after that first monster example, here's our last example on section 3.5. This example is going to be a little bit easier because we're given the function, its first derivative, and its second derivative already calculated out, and we just need to process these derivatives in order to determine all of the function behavior as we did in the last problem. So first, let's figure out the domain. We're going to figure out the domain by taking a look at the original function, and in this case there are no domain restrictions of the original function. We don't have any negative exponents or division by x, so we don't have to worry about any division by 0 problems. And our root here is a cube root rather than a square root, so we don't need to worry about any issues with negative numbers either. All in all, that means that our domain is negative infinity to infinity. Now, right away, if you notice here that both the first derivative and the second derivative are going to have values that make their denominator 0 and thus make the derivative undefined, since we have the domain of all real numbers, those values in this case are actually going to be critical values, which is not what we typically see when we have zeros in the denominator connected to vertical asymptotes. For part B, we're looking for the x and the y intercepts. We're going to find the x-intercept by setting y equals to 0. That means that we're going to set the original function equal to 0. So we're going to have 0 equals x minus 3 times x to the 1/3, and we're going to go ahead and solve for x. Before we do any of the algebra, we can notice here that both terms have some version of x involved, and therefore x equals 0 is one of the solutions to this equation right away, and that's one of our x-intercepts. That's also going to be our y-intercept. Now to solve for the other x-intercepts, we can add the 3x to the 1/3 over to the left here, and then we can divide the x to the 1/3, and when we do that, we get 3 equals x to the 2/3, which we can then further simplify by raising to the 3/2 power to get that x isolated. And when we do that, we get x is equal to positive or negative 3 to the 3/2 power. And then the reason that we need to do the positive or negative there is because when we're raising it to the 3/2 power, that's like taking the square root here, with the 2 being in the denominator of that fractional power. So our other x-intercepts then are x equals 3 to the 3/2 power, or x equals negative 3 to the 3/2 power. And if we wanted to do a numerical approximation of that, well, 3 to the 3/2 is the same thing as 27 to the 1/2 if we cube the 3 first. Oops, to the 1/2 there. And then 27 to the 1/2 is close to 25 to the 1/2, and that is equal to 5. So we can say that this is just a little bit bigger than 5. And we can see here that the numerical square root of 27 is actually 5.1, so we were pretty close with our estimate. That'll be useful for when we're trying to choose our test values. All right, so now let's find the y-intercept by setting x equals to 0, or evaluating f of 0, which we're going to do by plugging in a 0 everywhere we see an x in the original equation. And when we do that, we get a 0 there. And together, this intercept at x equals 0 and then the intercept at y equals 0 tell us again that we go through the point 0, 0 together. Now, let's figure out if this function is odd or even by evaluating f of negative x. And to do that, we need to plug in negative x for each of our x variables, and since each of these individual terms is an odd function, we get negative x plus 3x to the 1/3, and overall, if we pull out a negative here, we get x minus 3x to the 1/3, which is in fact negative f of x, which tells us that f is an odd function, and therefore f is symmetrical around the origin. And now if we take a look at the graph, we'll see that we have our intercepts at x equals 0 and close to 5 and negative 5. We have a y-intercept at y equals 0. Overall, that means that we go through the origin, and we should have rotational symmetry around the origin. So let's take a look at that graph. We see here that this graph of the function does meet all of those criteria. So let's take you back to the work here. I'm going to give you a second to pause to jot down any notes. All right, part D in this problem is going to have us try to figure out where the function is increasing and decreasing, and then using that information in the first derivative test, we can tell where it has local maxes and local mins. Note that the derivative is given to us in this problem, so we don't need to go through the work of calculating the derivative. We just need to do the analysis with the derivative. That's really nice. So the thing that we need to do with the derivative first is we need to find the critical values. And we're going to find the critical values by setting the first derivative equal to 0 and figuring out where the first derivative is undefined. The reason that the undefined points in the first derivative are going to be critical points in this function was because our function is defined on all real numbers, which we found up here. The domain is all real numbers because there are no zeros in the denominator of our original function. So what we basically need to do here is we need to figure out where the numerator is equal to 0 to figure out where the derivative is equal to 0, and where the denominator is equal to 0 to figure out where the derivative is undefined. So let's work with the numerator first. We have 0 is equal to x to the 2/3 minus 1. And we can solve that by adding 1 to both sides. And then we can raise to the 3/2 power to eliminate the exponent on x, which gives us that x is equal to plus or minus 1. Again, we need to use the plus or the minus here because we're taking a fractional root with a 2 in the denominator, which means we're taking a square root. So we have critical values at 1 and at negative 1. Then for the denominator, we're going to set 0 to be equal to x to the 2/3, and that just gives us that x is equal to 0. So we have 3 critical values then. Critical values at x equals positive 1, at x equals negative 1, and at x equals 0. Now what we need to do is we need to move this information to a number line so that we can test the subintervals in between our critical values to determine if the first derivative is positive or negative on those subintervals to figure out where it's increasing or decreasing. So let's go ahead and draw our number line here. Our number line in this case is going from negative infinity to infinity because we have no points where the derivative is, or where the original function is undefined. And then we have critical values at x equals 1, x equals 0, and x equals negative 1. And I forgot to change this one to a negative 1 right there. And then these critical points subdivide the interval from negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. And as I showed in the last example, I'm going to organize my testing on a table like the one shown right here to the right. And I'll give you a second right here to copy down this table. Alright, so hopefully you got that copied down. And now what we're going to do is we're going to test points in each of these intervals in order to determine the sign of f prime. So points, I'm actually going to want to choose things here that are easy cube roots so that my numerical computations are a little bit easier. Like -8, -1/8, +1/8, and +8. You can choose other numbers, but the cube root of 8 is 2, and that's going to make our numerical calculations a little bit easier here. So on this first test point, at -8, if we plug that into the derivative, we're going to get a +4 minus 1 all over +4, which is of course 3/4, which is a positive number. Let's go ahead and expand our table just a little bit so we can get that all to fit inside of our table right here. And then if we calculate the first derivative at -1/8, this might be a little less comfortable for you guys because it's a fraction, but we're going to get 1/4 minus 1 all over 1/4. And if you take a look at this, the numerator is going to be a negative number and the denominator is a positive number. Overall, we're going to get a negative number there. The same thing is true when we evaluate this at +1/8. We still get 1/4 minus 1 divided by 1/4 because the 2 in the numerator of the exponent is going to eliminate those negative signs, and we're going to be left with just the cube root squared of 1/8 there. So we get another negative at 1/8. And then finally, the calculation for f prime of 8 is the same as a calculation of f prime for -8 because we still get 4 minus 1 over 4, which is 3/4, and that is a positive number. So let's go ahead and transfer those positive and negative parities to our original number line here. This is a number line of f prime. So we have increasing from -infinity to -1, and from 1 to infinity, and decreasing from -1 to 0, and 0 to 1. Using this information, we can write down that f is increasing on the interval -infinity to -1 in union with 1 to infinity. F is decreasing on -1 to +1. We include x equals 0 here because x equals 0 is in the domain. In fact, x equals 0 is where the derivative is undefined, which can mean that we have a vertical tangent line. And we can take a look at the graph and see that. So that we have a vertical tangent line at x equals 0, and then we have these intervals of increase on the ends, and it decreases in between 1 and -1. So let's take a look at this work again, and there's one last thing that we can determine from our number line with the first derivative. We can tell that the critical value at x equals -1 is a local maximum, and the critical value at x equals +1 is a local minimum, and we can also tell that the critical value at x equals 0 is neither a max nor a min. So we have a local maximum at x equals -1 and a local minimum at x equals +1. Again, let's take a look at that on the graph really quickly. So we can see here that we have the local maximum at x equals -1 and the local minimum at x equals +1. And now I'll give you a chance to take down some of these notes. All right, let's keep cruising on here. Part E is asking us to find where the function is concave up, concave down, and identify any inflection points. And we're going to do that by using the provided second derivative, 2 over 3x to the 5/3. To answer these questions, we're going to do the exact same process that we did with the first derivative, but with the second derivative. And instead of finding critical points, we're going to be finding the possible inflection points. So as with the first derivative, we're going to find our possible inflection points by figuring out where the numerator is equal to 0 to determine where f double prime of x is equal to 0, or we're going to figure out where the denominator is equal to 0 to figure out where f double prime of x is undefined. And we're only going to include these points if they're in the domain. So we're not going to include our vertical asymptotes, although we would put our vertical asymptotes as cut points on our number line when we're trying to determine the intervals of concave up and concave down. All right, so first, where is the numerator equal to 0? Well, never, because 2 can never be equal to 0. So we don't have any points where the second derivative is equal to 0. However, we do have points where the second derivative is undefined. In fact, if we set the denominator equal to 0, we're going to see that at x equals 0, we have an undefined second derivative. This is similar to a critical point, but it's not a critical point. In this case, it's not a critical point, it's a possible inflection point. And we'll tell later if it's an actual inflection point if the concavity changes at x equals 0. The way that we're going to determine that is by, again, doing a number line. We're going to put x equals 0 on our number line as our only possible inflection point. And we don't have any breaks in the domain, so we should have the same sign for the second derivative on each of these subintervals from -infinity to 0 and from 0 to infinity. So again, let's make a table to organize our work. So we only need 2 rows in our table this time because we have the interval from -infinity to 0 and from 0 to infinity. Good test point values would be -1 and +1. And then if we go ahead and calculate our second derivative at -1 and +1, we're going to see that we do have a change in concavity. So f double prime of -1 is equal, because we have odd numbers in this fractional power, which means that the negative won't get eliminated by some kind of a squaring function. And so we're going to get 2 over -3, which gives us a -2/3. And if we plug in f double prime of +1, we're going to get a +2/3. So we're going to have a concave down function from -infinity to -0, and a concave up function from 0 to infinity. I'm going to go ahead and pause that right there, and then we're going to take a look at a graph to see what this looks like on the graph. Alright, so let's take a look at the graph again, and you can see that this function is in fact concave down from -infinity to 0, and then it's concave up from 0 to infinity, and we do have our inflection point there at x equals 0, where the concavity changes from being concave down to concave up. That's that squiggle shape that we should expect when we're looking for inflection points. So for part F here, we're going to need to pull together all the information that we've determined so far. We want to get it all on the same sheet so we can sketch the graph. So first, I've written down all the information that we get from the algebra. We know that the domain is -infinity to infinity. We know that the y-intercept is x equals 0. We know that our 3 x-intercepts are x equals 0, x equals 3/2, x equals -3 to the 3/2, which are approximated by 5.1 and -5.1, and the f is odd, which means that there's a 180-degree rotation symmetry around the origin. So let's go ahead and copy over our f prime graph so we can see our intervals of increasing and decreasing, as well as our extrema listed. And our graph of our second derivative, our number line of our second derivative, shows where our function is concave down and concave up. Then we can kind of combine these graphs to see that we have intervals from negative infinity to negative 1, and negative 1 to 0, and 0 to positive 1, and 1 to positive infinity. And from negative infinity to negative 1, our function is increasing and concave down, which is going to look something like this. And when the function from negative 1 to 0 is decreasing and concave down, it's going to look something like this. From 0 to positive 1, it's decreasing and concave up, which looks something like that. And when it's from 1 to infinity, it's increasing and concave up, which looks something like this. So let's use that information to sketch a graph of our function f. Our axes here, we'll go to -5 because that's where our intercept is going to be. And +5, let's go ahead and go up there like 3 or 4. And let's put our intercepts on the graph. So we're going to have intercepts at x equals 0 and at y equals 0. That's our origin. And we're going to have y-intercepts at a little bit less than -5 and a little bit more than 5. And we have a local maximum at x equals -1. We know that the y value there is 2 if we evaluated the original function at -1. And we have a local minimum at x equals +1, and the y value there is -2. Now, the graph is increasing and concave down from negative infinity to -1. So it must have this kind of a shape. It's increasing and concave down, reaching its maximum at -1. And then it's decreasing concave down until it hits this inflection point at the origin. After the origin, it's decreasing concave up until it hits the local minimum at x equals 1. And then from 1 to infinity, it's increasing concave up. So that's a sketch of the graph using the calculus. I'm going to go ahead and let you take a look at that for just a second. And we can see that our Desmos graph looks very similar to the graph that we came up with by using just calculus and our own brain power. And luckily, that's the end of our examples here for section 3.5. Have a great day, everyone.